All right. So last time we went through we introduced the normal, the Gaussian distribution, and how we can generalize the standard normal to the normal family of distributions with parameter mu and sigma squared. And we introduced at the very end the idea of how we can use the Gaussian distribution to approximate the binomial. We're going to talk about that in more detail here. So the normal approximation to the binomial says that, so remember, just remember that if in the normal family, right? Let me just put this in a different color here. In the normal family, mu is the expectation, sigma squared is the variance, okay? And so what we saw in the introduction of the normal approximation to the binomial was if we have a random variable x that is normal or that is binomial n and p, then as long as n and p are np and q are reasonable, a reasonable size, then x can be approximated by the normal distribution with mean np, which is the expectation of the binomial np, and variance npq, which is the variance of normal with binomial parameter n and p. And this is different from how we remember in the law of rare events, or the law of small numbers, the Poisson approximation to the binomial was when n and when p was really, really small relative to n. And in this case, we want p to be of reasonable size, and n times p is generally going to be going to infinity, as opposed to in the Poisson case where n times p is settling down to a finite value. Okay. So think about how this works, or why this works, is we're going to show it with an example. So let's do it with an example where we are going to spin a pointer 10 times. And the way this pointer works is it's actually a little bit of a simplification of the case that we saw before. Jeez. There. So what we're going to do is we're going to label each side as A, B, C, D. And we're going to spin the pointer, and we're just going to record which side does it point to. We're actually just going to record whether it points to A or not. Okay. And let's just assume these corners don't happen. It's an edge case. So spin a pointer 10 times with 4 possible outcomes. A, B, C, and D. Okay. And let's define n sub A to be the number of times that the pointer points to A, the side A. So it's that whole side. So we assume that this is well spun, so that all of the possible sides have equal probability of 1/4. And so this is going to be a binomial distribution. So the distribution of NA is binomial. We have 10 trials, and we have a success probability of 1/4 on each trial. And let's say we wanted to ask the question, what's the probability that n sub A is bigger than or equal to 4? Well, we know what the mass function is of n sub A, right? Remember, the mass function of n sub A is 10 choose k, p to the k, 1 minus p to the 10 minus k. So the probability that this random variable is bigger than or equal to 4 is the sum of all values of k bigger than or equal to 4 of that probability mass. Now, this is certainly not hard to do. These things can get very cumbersome to do, but in this case, there's only 7 terms in this sum. We could certainly do this for ourselves, and if we do, we get that this value is about 0.224. Okay, but what we want to do is we can actually do this much more simply, and especially in cases where the number of trials is much larger and this sum would be really prohibitive. We can do this using the normal approximation. Okay, so the way to look at this, or the way to visualize this, is to imagine that we have the masses of n. Okay, so the possible values of n are all of the values of 0, 1, 2, 3, etc. All of the integers from 0 to 10. And there's a probability mass associated to each of those. So what we're going to do is actually we're going to put it here. We're going to draw a probability histogram. So the probability histogram is going to be a histogram where we draw a box around each possible value of NA. And it's going to go from halfway to the left and halfway to the right. And the height is going to be the probability mass. Okay, so it's going to look something, be a little more careful here, but try to have these be pretty straight. So that's not halfway between. Okay. We'll explain why this is in these aren't necessarily drawn to scale, but giving you the idea that the binomial with 10 trials and probability a quarter looks something kind of like this. Okay. Jeez, wants to connect to that one. Can't lie. Okay. So the probabilities become very, very small as we get close to 10. And what we're interested in is we're interested actually in probability that n sub a is bigger than or equal to 4, which is the sum of all these probability masses. Now, what I should point out is that, okay, what we're doing is we're putting a rectangle. So we're putting a rectangle around each possible value, and the height of the rectangle is the probability mass. It's the mass of that point. So that means that the rectangle above each point has height, which is the mass function, and width or base of 1, right? Because it goes from half to the left, half to the right. And therefore, it has an area. The area under the curve, the area of each rectangle is the probability of that point. And what we would see is that if we superimpose the normal distribution on top of this, and that's not necessarily a great rendition of it. Let me do this. Jeez, not cutting this. All right, something like that. That the normal, let me do it in a different color. So the normal distribution with mean 2.5, which is the mean of the binomial, and variance 1.37 is close to the histogram. Now, how close is it? Obviously, by the picture, it doesn't look that close, but really what we want to know is we're interested in the probability of n sub a being bigger than 4, bigger than or equal to 4, which in this histogram is actually the area under the histogram of the rectangles that go from 3.5 up to 10.5, or really 3.5 up to infinity, because the probabilities are just 0, and you can think of those as rectangles with height 0 and therefore area 0. Okay. So if we approximate x by the normal with the corresponding mean and variance, and compute the probability that this normal distribution, okay, let's call it D, okay, the probability that D is, so probability that NA is bigger than or equal to 4 is approximately the probability that D is bigger than or equal to 3.5. This is called the continuity correction. And that comes into play by looking at how the histogram compares to the underlying probability, how the histogram gets drawn, where the way that we think of the histogram is actually as a density. It's like a continuous density for the binomial, where the probability mass around a point gets spread out in this rectangle, right? And in this case, the lower limit here becomes 3.5, because we want to go above 4, which is above 3.5. Well, if we do that, since this is being since D is a normal with mean 2.5, variance 1.37, then if we normalize it, so we normalize left, we normalize right, then on the left-hand side now, we have a normal distribution standardized. Hold on a second. Okay, so I made a typo here. The variance is actually the square. So it's 1.37 squared. And so the standard deviation is 1.37. When we normalize in this way, this is, of course, just a standard normal. So this is the probability that z is bigger than or equal to 0.73. And this is the probability above z. So the cumulative distribution function phi is the probabilities below a certain value. So it's 1 minus phi of 0.73, which we can look up in a table, or we can use a calculator to get 0.233. It's close. It's not exact to what we calculated up here, but we see that it does give us an approximation. And it's oftentimes easier to calculate this than it would be to just to brute force sum through the masses of the binomial. Let's go through another example. Some kind of marbles example. So what we have is a large collection of marbles. And they have diameters. So each marble has a diameter that are approximately normally distributed with a mean of 1 centimeter. And we also know that 1/3 of the marbles have diameters greater than 1.1 centimeters. Okay. So what can we say about this? Well, we haven't been told the standard deviation, but we've been told something about the probabilities, right? And we know what the cumulative distribution function is for a Gaussian. So first question we would ask is, how do we derive the standard deviation from this information? Okay. Well, what we've been told is that there's a mean of 1, and we've been told that 1/3 are above 1.1. Okay, so that tells us that 2/3, right? So then 2/3 are less than or equal to 1.1, right? So in this case, we're saying that X is approximately normal. It has a mean of 1, and it has an unknown standard deviation. And we've been told that the probability that X is less than or equal to 1.1 is 2/3. So from that information, what we can say is, well, we can look up what is the quantile in the standard normal, how many standard normal random variables are less than or equal to 2/3? Or sorry, what is the value at which a standard normal has probability of 2/3 being less than or equal to is 0.43. Okay. And then what we're going to do is we're going to reverse engineer what sigma would have to be in order for this to be 0.43. Okay. So we know that this here is standard normal in the case where we subtract off the mean and we divide by the standard deviation, and this would be equal to 2/3. And we know that this has to be 0.43 for that to be the case. So the solution is 1.1 minus 1 over sigma. It's 0.43. Tells us that sigma has to equal 0.1 over 0.43. So it's about 0.23 centimeters. Okay. What fraction of the marbles have a diameter within 2 centimeters of the mean? Okay, so the diameter now has to be within, oh, I'm sorry, 0.2 centimeters. Has to be between 0.8 and 1.2. Okay, so let's do this. So let's let the diameter be D. So D is going to be normal with mean 1 and standard deviation and variance 0.23 squared. Okay, so we want to convert this to standard units. So we get 0.8 minus 1 over 0.23. And the reason why we do that is because when we do that to the random variable D, we convert that random variable into a normal 0, 1. And so this becomes the probability that a normal 0, 1 is between negative 0.86 and positive 0.86. And we can now express this in terms of the cumulative distribution function of the standard normal. And the way that we have to do that is we realize that this is equal to, first, we have the probability that Z is less than 0.86, but then we want to get rid of the probability that Z is less than negative 0.86. All right, so just to visualize here, we're interested in, this is negative 0.86. This is 0.86. So we're interested in this green area. Okay. So that's what this is here. Okay. But what we can do is we can actually first calculate this pink area, which is everything in green, but also everything less than negative 0.6, right? So that's what this is. And then what we have to do is we have to subtract off everything less than 0.86, which is the purple area. Now, by symmetry, what happens is that phi of negative 0.86 is the same as 1 minus phi of 0.86. So so the amount of mass to the left of negative 0.86 is equal to the amount of mass to the right of 0.86. And the reason we do this is because we just express everything. So back in the old days, you used to have to look this up in a table. Now you can still look it up in a table, but most calculators and computers will calculate any of these values for you. So you don't technically need to do this to be able to calculate, but it used to be that you had to express this in terms of the distribution function evaluated a positive argument, and you would have to use symmetry to be able to do that. But we do this, we get 61%. And then final question for this exercise would be, what diameter is exceeded by 75% of marbles? So for this, the value in the standard normal is negative 0.675 standard units. So that means that for our sake, D of 75, the value that we're looking for, is going to be, well, it's sigma Z of 0.25 plus mu. Sigma is 0.23 times negative 0.675 plus mu, which was 1. And we get an answer of 0.84 centimeters. Okay. So that's a little bit of how we work with the normal distribution, and we'll see plenty of a lot of the same logic, but there are some special properties, and in particular, the value in approximating distributions. In this case, we saw it for the binomial, and we would see it. We'll see it plenty of other examples as we move through.